Thank you, Dr. Michaels. Our next presenter will be Dr. William Cotton. Dr. Cotton is professor of the Department of Atmospheric Science at Colorado State University. He's been on the faculty since 1974. His professional research experience includes work as a meteorologist in the Experimental Meteorology Laboratory, ERL, National Oceanic Atmospheric Administration, and Department of Commerce. He also has served as head of the Numerical Simulation Group and has received numerous awards over his career, and is a fellow of the American Meteorological Society and the Cooperative Institute for Research in the Atmosphere at Colorado State University. He's published more than 160 papers in peer-reviewed journals, 10 chapters in books, authored 1 book, and co-authored 2. Dr. Cotton.
Well, thank you. It's my pleasure to be here. After listening to talks this morning and the luncheon today, I think I must be the most liberal and green person in this whole meeting. I voted for Obama. I own 2 hybrids. I bicycle 13 miles to and from work. I paddle a kayak, sail a boat, and fly a sailplane. So I think I'm pretty green. But this isn't about my politics. Actually, another thing strike against me, I'm a modeler. But anyway, this isn't about politics, this is about science, and that's my thinking, is about science. And the talk is based on a chapter of a book that was organized by the Franklin Institute in Frankfurt, Germany. It's Clouds in the Perturbed Climate System, the Relationship to Energy Balance, Atmospheric Dynamics, and Precipitation. And I was asked to write a chapter on weather engineering or weather modification and geoengineering. And so I called it Weather and Climate Engineering as such. I don't think the organizers really knew what they were getting into, because I wrote this from the perspective from a person who was rather skeptical about anthropogenic greenhouse warming. And, from the perspective, if it ain't broke, don't fix it. And in fact, when I completed the draft of that and submitted it to the editors for a publication, they went through and edited out anything in there that was skeptical about greenhouse warming. And I referred to that as blatant, I had to write it down because I keep censorship. Couldn't think, I have a hard time remembering that. Anyway, I referred to that as blatant censorship, and I said I'm going to withdraw this paper from that book. And the organizer actually, she came back to me and said, oh no, don't do that. I actually had another publisher who was going to publish it. And this just kind of illustrates the climate, whereas, if you say anything against greenhouse warming, well, you're out of there, Anyway, so I'm going to talk a little bit of an overview on this. I've had a lot of reactions to this kind of talk. Tony Slingo, the late Tony Single, actually referred to this as being wicked. Graham Stevens, my colleague at Colorado State, refers to it as wacko. And actually, one person recently has referred to it as wonderful, so I can change that. Deliberate cloud seeding with its goal to increase precipitation or reduce hail or to reduce the intensity of hurricanes and so forth has been around for over 60 years. And it began following the experiments of Irving Langmuir and Vincent Schaefer. Actually, Vincent Schaefer was a mentor of mine. And for many years, weather modification was highly visible in the news media. And most of the research in clouds and storms work, which is what I've been doing for years, was linked in some way to weather modification in the early years. Hence, this is my background and training in it. I remember as a here's just an illustration of some of the Schaefer's seeding experiments of Strata Cumulus off to the east of Albany, New York. Super cool Stratocumulus, and you can see the general opening of the Stratocumulus field by seeding in this area here. Incidentally, I said it was very, very much prevalent in the news media, not quite to the extent of greenhouse warming, perhaps, but it was enough so that when I was about 8 or 10 years old, Donald Duck was actually involved in cloud seeding and that. And so there were, comic books with actually in it. So it was getting a lot of press and a lot of visibility. If we look at cloud seeding, they're basically broken down into glaciogenic seeding and hygroscopic seeding. That is where you introduce materials like silver iodide or dry ice into supercooled clouds and then try to convert them more rapidly to ice particles and then eventually precipitation. And the other is using salt particles and not different types of salts to enhance the collision and coalescence process in clouds and that. Well, anyway, if you look at it over the years, we found that there's been very difficult to document increases in precipitation on the ground due to glaciogenic seeding of cumulus clouds. On the other hand, there's been more significant success in trying to show that seeding orographic clouds, like in the western U.S. and that, can cause increases in snowpack. So there's some pretty convincing evidence in that. The hygroscopic seeding is basically the inverse of if we have clouds that are infected by anthropogenic pollution aerosols and that. In that clouds, hygroscopic seeding has introduced ultra-large particles, which can enhance the collision and coalescence process, whereas pollution produces large numbers of very small particles, which actually inhibits the collision, coalescence, and warm rain process in that. The results of more recent studies on that are really quite promising, and a lot of people are quite excited about it. Recent National Academy report actually emphasized the optimism from those studies. But still, they did not really demonstrate what we call proof that seeding those clouds can increase rainfall over a specific area on the ground. Well, the main purpose of going through this is, what do we learn from that? Well, first of all, the scientific community has established a set of criteria that we require that there's proof that seeding enhanced precipitation. And for proof that we require that there's both strong physical evidence of appropriate modifications to cloud structures and highly significant statistical evidence is required. So I argue that basically that proof that climate engineering, if we get to that stage, or even that human-caused CO2 is a modifying climate, we require that there's both strong physical evidence that are modifying climate as well as the statistical evidence. And this is where I get into the rub with some of the greenhouse people. Another aspect, lesson learned, is that there's the evaluation of cloud seeding experiments and studies is at the mercy of natural variability of the weather systems and that. And so it's been very difficult to identify strong cause and effect because of this large natural variability. And I argue from the same can be said about climate engineering, or even that human-induced CO2 is altering climate. If the strict signal is not strong, and it is not that big a signal, then to evaluate if human activity has produced some observed cause and effect, one requires a much longer time records than we have in terms of actually measurements with modern-day sensors and that. So I argue we really don't have a really good measure of what the natural variability of climate is. So venturing into climate engineering, recognizing these large natural variability, I think is pretty hazardous. So I probably don't need to go through this, but I'm just going to highlight these. If we look at greenhouse or climate forcing factors, we talked about water vapor and how it's an important feedback, and that's the major greenhouse gas, whereas CO2 and methane are secondary to it. Changes in luminosity, orbital parameters is other things. Changes in surface properties due to land use and that. Natural and human-induced changes in aerosol and dust. This is the area that I work in quite extensively. And volcanoes, particularly desert dust and that, as well as different temporal responses to external forcing by the atmospheric oceans and that. So this leads to a source, by the way, of natural variability here that is not really well captured in a lot of the models. Here's a figure that Warren Washington provided me. He gave a seminar in a department a week or so ago. And this is with the DOE coupled ocean model. It's a deep ocean model, not just a surface mixed layer model and that. It's probably one of the most elaborate models there is. And on this figure here, just looking through from 1900 to 2000, just looking at the predictions of the model against the observations in that. And this does include volcanoes, by the way, Pat. This is not forecast of that. This is basically putting in volcanoes when they're observed and that. And this allows the model to actually replicate a fairly significant dip here, for example, for Peninsula and that. And that. And this is versus if they remove the anthropogenic aerosols, they get this. And this is pretty convincing. It's a pretty convincing figure that anthropogenic anthropogenic CO2 is playing an important role. But remember, this is only through 2000. The record that we've seen, Pat showed this, that if you look at the observed, it's pretty flat after that. Can this model reproduce that? Well, the problem is there's no known forcing that can account for that flattening of the curves, the temperature curves in the last in this century, actually. So the modelers are now saying, well, it must be due to natural variability, and that, but they can't really account for that. The model doesn't experience that kind of variability in that. At least we don't think it does. I haven't seen the results that suggest that. The other thing is that projecting the future, the models can't predict volcanic activity. There's no predictability on volcanic activity, yet that was important to actually give them a good representation of the climate or the mean temperatures during this period. So keep that in mind. Some of the hypotheses for modifying the climate basically are essentially, let's emulate volcanoes. Let's introduce sulfur dioxide and hydrogen sulfide into the stratosphere by some mechanism or other. This will undergo slow gas to particle conversion and produce essentially spheric acid droplets, which then scatter solar radiation, and that would have a cooling effect. Crutzen also, among others, had suggested, well, maybe using black carbon in the stratosphere would also have an effect. Black carbon doesn't scatter the solar radiation, but it absorbs it, leads to heating in the stratosphere, which is a concern because it might affect the stratospheric circulations and that sort of thing. But it's much less expensive, actually, to put in black carbon in the stratosphere than it is to put in sulfur and so forth. You get much more bang for your buck. Some of the other hypotheses, well, let's see the stratocumulus clouds. One of the nice things about stratocumulus clouds is they reflect incoming solar radiation. They lead to a cooling impact. So any place there's subtropical highs in the world, where there's subsidence, and that you can experience large areas of stratocumulus clouds in that. And these are cooling the planet. So John Latham and colleagues have proposed building a fleet of these ships that are spinning towers and that produce sea spray. And these sea spray are producing, when the sea spray evaporates, produces small droplets, which then, and when they enter into the clouds, you make more numerous small droplets in the clouds, that'll increase the albedo. And incidentally, these spinning towers actually propel the ship because using the Magnus effect, they actually act like sails on these proposed ships. So we'll build a couple thousand of these things. Another possibility is to seed black carbon aerosol in cirrus layers. This is basically, it has the advantage that the black carbon aerosol absorbs solar radiation, warm the layer, drive the vapor pressure below saturation in those levels, so it makes the clouds more transparent to infrared radiation, as well as during the day absorbing solar radiation, so that it has a double benefit in terms of cooling. So that's kind of interesting. How you go about it economically and doing widespread over the globe, that's a big question. I don't know how you do that. Some other proposals, deploying something like 50,000 to 55,000 mirrors in space, or introduce a big reflector at the Lagrangian point at the Earth. The costs are extremely high, and then the one problem with this is that once you've got them out there, and if things start cooling, that we get into a period of, say, volcanic activity and that, how do you turn them off? You know, you got to go up and and try to get those away. Whereas, at least with the particles, you know they're not going to stay around for more than a year or two. So that's not a problem. There's been a lot of discussion. Alan Robach, for example, had a list of some 20 reasons why we shouldn't do climate engineering. One of the biggest ones is that it could have impacts on the hydrological budget and that. And we've seen that the hydrological budget is important to greenhouse warming. That is, the vapor content of the atmosphere, the clouds and so forth play an important role in the radiative budget of Earth. They could have consequences in terms of ozone depletion. One of the things, if you're successful in producing the cooling, then you might end up heating more and producing more fossil fuels in that, so that'd be a negative feedback in that. And if it goes all right, can it really be turned off in that? Just some of the highlights of those ideas. Well, NASA's been doing climate engineering for some time now. You can see that by putting all the space junk in here, that this is probably enough junk to start cooling the planet as well. So anyway, why do we want to do research on climate engineering? Well, you know, in the cloud seeding area, you know, we realized that, well, science in cloud weather modification essentially terminated in the late 1980s. But this has not stopped operational cloud seeding. It's done throughout the U.S., principally in the western U.S. It's done in China. It's done in a lot of other countries and that. A lot of expenditures go into cloud seeding, in spite of the fact that the science has not progressed very much. Well, in fact, most of these operational programs are what I call political placebo. Let's do something because we've got a drought. So we got to do something about it. Well, I think that if we find ourselves in a real climate disaster, whether it's human caused or not, if things are going too warm, too cold, or whatever, that politicians are going to call for implementation of climate engineering strategies. And my argument for doing the research is, if they're going to do that, I'd like to see them do it with the most advanced scientific knowledge of what's happening, and also the consequences of that, rather than, well, let's go out and do it anyway. We've got to have something done and spend billions of dollars to implement climate engineering with really a very poor scientific basis in that. So that's basically my argument of why to do research on climate engineering.